You can start.
Okay. Yes.
The mic is here.
Oh. Sorry. Welcome everyone. I'll be talking about EVM workloads in the wild. My name is Lioba Heimbach, and this talk is largely based on joint work with Kushal Babel and Jason Milionis, and we're all at Category Labs. So this talk is generally motivated by two problems that we generally have with the EVM or the EVM pricing today. The first is that gas, as we have it in the EVM, it collapses many different resources, so CPU, storage reads, storage writes, bandwidth, and more, all into one single number. This is generally fine if our workload mix stays the same, but if it doesn't, which maybe we would expect with different chains that all use the same EVM, or even on the same chain as it evolves over time, it isn't fully fine anymore, because it will mean that if the resource mix shifts, but the relative pricing all stays the same, that some resources will be underpriced. Now, the second problem is that the state of the EVM evolves. So when you go and you submit a transaction, in all likelihood, you simulate your transaction on the current state that you have available. But in all likelihood, there will be blocks or maybe just transactions before you in the block where you will be executed that execute before you and move the state. And with that, it is also not unlikely that your transaction will have a different outcome than it had during the simulation. So both of these problems, they stem from, at least in my opinion, the same assumption which the EVM makes. That is that execution conditions are largely stable. And we measured sort of to which extent they are. For that, we have two data sets. So we collect a data set of yearly data from the Ethereum layer 1 and the Base layer 2 to have an example of a high throughput EVM chain. And for both of them, we sample 3,000 blocks a day. That gives us around 220 million transactions on Ethereum, and it gives us 275 million on Base. And then for each of these transactions, we go ahead and we simulate them again. Through that, we get the gas decomposition. So we get like what opcodes were actually used by these transactions, and we can break down the gas usage in terms of how much of the gas usage went to compute, how much went to storage reads, writes, and so on. Then for all of these transactions, we also measure their individual storage growth. So did they create new accounts? Did they write to new slots? Maybe they even deleted slots. And did they add new bytecode? And if so, how much? We also then classify all of these transactions, like is a transaction MEV, is it DeFi, and so on, to be able to make statements later on by category, because the profiles of these transactions vary wildly depending on whether it's MEV or a simple transfer, for example. Then we also have a second data set, which is more the state sensitivity data set, and we have that for the September month of 2025 as well, so for the same set of daily blocks. And essentially what we do here is that if we have a transaction that executed at position I in block B, we will also simulate this transaction as if it were executed at the beginning of block B. So instead of position I, at the beginning of block B minus 5, B minus 10, and B minus 20, and so on. And essentially what this allows us to do is to see how this transaction's execution differs as we execute it on like older and older state, essentially. So the same transaction, just executed on different state, how does the behavior change? And here, in addition to our full year data set, which we have for the workload, we also record in addition like exactly which storage slots are being read and exactly which are being written to. So let's start with the first problem, which is that the workload mix is not stable. So to see why under these conditions, maybe it is not it could be a problem that we collapse all these different resources into one single number, I want to go through like a sample transaction. So we have a Uniswap free swap here that swaps USDT to ETH. And it was on Ethereum in January 1st, this transaction. And I just went ahead and like looked a bit at what opcodes was this transaction actually using, like what physical resources was it using. So this transaction did 10 as store operations, so that's writing to storage. It did 18 as load operations, that's reading. It had 805 bytes of call data, that uses bandwidth. And it emitted 5 logs during its execution. So we have all these different resources that have different costs to the network. But what the EVM does in its gas metering, it just takes this and it collapses it into one number. So here we have in the end 156,000 gas. That is all sort of that the EVM will see when scheduling, and what I'm showing in the bar below, like how much of that is writes, how much of that is reads, how much of that is compute, that is hidden to the EVM when it's scheduling. And yes, so having this translation from all these physical resources into one unit of gas, it works if your workload mix stays roughly constant over time, or otherwise you would need to adjust. And we wanted to see to what extent the workload is the same both across chains and within the same chain. So first, let's compare how sort of the workload is different on Ethereum, the Ethereum layer 1 versus the base layer 2. So on Ethereum, as you can see on the slide here, I'm showing sort of the gas breakdown by category, like how much gas was spent on storage, writes, reads, and so on. And in general, you can see that the Ethereum layer 1, it's pretty write heavy. Around 34% of all gas usage went to storage writes. If we go to the base layer 2, on the other hand, only around 25% went to storage writes. Instead, on the base layer 2, we see that it's more read and compute heavy relatively, where we have around 30 and 25% going to reads and compute, and less so, more so than it on the Ethereum layer 1. So these two chains, they both are EVM chains. They have the same opcode prices, but they have very different workloads. Like the same translation can't work for them both. But it isn't only that we have different profiles on different chains, we also have different profiles on the same chain. So what I'm showing on the slide now is just the breakdown of gas on 2 days on the Ethereum layer 1. I'm comparing a day in January to a day in December. And you can see that the writes went from around 34% to 20%, and the compute went from 17.5% to 37.5%. So this is the same chain, again, the same prices, and again, a vastly different research usage that we have here. And it is a problem if we have these fixed prices, but a moving workload. So to illustrate that, let's look at the figure that I'm showing here, and essentially you can see on the graph like the gas share of reads and the gas share of compute, and like each dot is one of the 2 days on Ethereum we just saw. And the star is sort of where we assume the ratio to be when we're setting prices. Like it can only be at one point in the space. Let's just assume it is at the point that is shown. And then the distance between this fixed price that we're assuming and what we see on an actual day is how wrong it is on that particular day. One side effect of this, for instance, is that blocks will appear full, while like individual resources will still have headroom. So we're mispricing something here if we're not meeting the desired ratio. Another thing, or like one reason why this might be happening on Ethereum, that we're seeing these different resource mixes on different days, is that Ethereum actually went through some scaling in 2025. So we went from a 30 million gas limit to a 60 million gas limit. But largely the opcodes were not repriced, and the implicit assumption behind this is that in each research dimension then grows uniformly, essentially. And what we then did is like we just wanted to see, okay, if we compare January, which was before the increases, and December, which was after the increases, we doubled the capacity, but in doing that, we actually tripled compute, while reads only grew by 1.65%, a factor of 1.65 in terms of gas usage. So that means that if we have like a uniform capacity increase, it does not necessarily produce a uniform resource growth. At the same time, though, maybe we also don't always want this uniform resource growth, because while CPU and I/O, they're like per block cost, we execute something, then we're done with it, we can forget about it. State is permanent. So every slot we add, every node needs to keep it forever, and then if the state were to rise uniformly, doubling capacity would also double the rate of permanent accumulation. So we looked at the storage as the state growth on both Ethereum and Base, and essentially On Ethereum, the state grew by, extrapolated from the 3,000 blocks we have, around 35 gigabyte in 2025 and around 440 gigabyte on Base. Now, when we again look whether the state growth goes uniformly with the gas target increase, we see that it actually outpaces it. So it grows by, while on Ethereum, the gas target went a factor of 2 between January and December, state growth went by a factor of 3, and for Base we see a similar pattern. But arguably, state is actually the one resource where maybe you want to grow it to grow less than proportionally when you're increasing your gas target, but like with this 1D gas, it is very difficult for you to target that. We can also see where the state growth is actually coming from, which is quite different on the two chains. So on Ethereum, it's largely coming from account state. And interestingly, 30% of all state growth on Ethereum is coming from simple transfers that transfer ETH to like a new account. And there's no surcharge for this, they just pay the 21,000 base gas essentially. There are already IPs being proposed to address this discrepancy. Then if we go to Base, on the other hand, we see that much of the storage growth comes from storage slot and contract bytecode. And here the main culprit is the Zen token, or like one of the main culprits, where we have one contract that is only accounting for 0.03% of all transactions, but responsible for 12% of the entire storage growth. So again, you can see that they have very different profiles, Base and Ethereum, but again, we're using the exact same opcode prices for both of them. So that brings me to the second problem, which is that transaction behavior varies. So let's look at maybe how a transaction, like a DeFi transaction, looks on Ethereum. And again, we have a sample transaction from September of last year. And we had a user here that wanted to swap 83 million Clanker for ETH, and they wanted a minimum output of 0.3705 ETH for it, and they specified this with their slippage tolerance. Now, as I mentioned before, when we're doing our state sensitivity analysis, we simulate the transaction on historic states. Like in comparison to the block where it was actually executed, how would it have executed 20 blocks ago, 10 blocks ago, 5 blocks ago, and at the start of the same block? And you can see that for this transaction, it would have succeeded for all of these lookbacks. At the start of the block, it would have received 0.3812 ETH, and this is more than it wanted with the slippage tolerance, and it would have executed successfully. However, it wasn't at position 1, it was at position 27, and there was another transaction at position 25 in the same block that did a swap in the same pool in the same direction. It moved the price by around 5.5%. As a result of that, since there wasn't too much liquidity in the pool, the transaction now would have received only 0.36 ETH, which is lower than the slippage tolerance that was specified, and the transaction ended up reverting, still executing on-chain and using some gas. Now, this all is probably not surprising to you. We all know that this is happening to DeFi swaps, but I think the point is here, like, we wanted to understand how sensitive are transactions to the state, like how often does this happen to transaction, and by extension of that, like what is the impact on users? So the simplest thing you can do to figure out, like, are transactions sensitive to the state, you just look at the gas usage. If I execute them on different states, do they use the same amount of gas or different amounts of gas? If the number is different, something at least slightly different was happening. So we compare the gas estimates for all the lookbacks, and we compare, and on Ethereum, we see that around 14% of transactions exhibit some sort of gas variance, while on Base, it's nearly 50% of all transactions where we see some gas variance. Now, we also look at this by category, and I think that's also no surprise to all of you probably, that especially MEV and DeFi, we see a lot of gas variance. Nearly 50% of all transactions on Base and Ethereum exhibit gas variance, while simple transfers, for example, exhibit almost no gas variance. Now, gas, all it does, if we see some variance here, it tells you that something changed, but it doesn't tell us much about what is actually changing. So we also wanted to look at that in more detail. And for that, we looked at 3 metrics. So for each transaction, at all of the simulations that we're doing, we're recording what storage slots is it accessing, so what is it reading, to which slots is it writing to. And then we also compare like what value it is writing. And essentially, what we then show here, what I'm showing on the slide here is the overlap. So between 2 simulations, what is the overlap of reads, what is the overlap of writes, what is the overlap if we wrote of the value that we're writing. And you can see that on Ethereum, actually, the most important line is the one that is highlighted in orange. This just shows you like the difference between the simulation at the start of the block, which that is like the state that the user in all likelihood, like that's the max state they have access to in all likelihood. They don't have access to the state after some transactions in their same block already when they're simulating during their submission, when they're submitting their transactions. So we see that the read overlap on Base between the actual and the start of the block is pretty high, same for the write overlap. But when we look at the actual values that are written, around 1 in 5 transaction writes a different value. So that means something changes in the execution. For example, they get a different price. When we move to Base, it's a bit of a different profile. The read overlap is pretty low. Write is again high, and for the values, around 1 in 3 of them write a different value to a slot. So generally, like transactions are quite sensitive to the state, especially MEV and DeFi again, which we look in more detail here. So this is again a comparison of the actual execution versus the start of the block. And you can see that on Ethereum, like MEV across all categories has a bit of an overlap of between 70 and 80%, while on Base it's very high for reads at almost 100% and very low for the values at around half. So only half of the writes that we're doing are actually writing the same value. While for DeFi, the profile looks very similar on both of them. In general, they're reading the same slots, the transactions, if we execute them on a bit of an older state, but 1 in 3 write a different value. So all this variance, I mean, for MEV, we're really anticipating it. But we are also, to a lesser extent, anticipating it to DeFi, but at that point it becomes a bit of more of a UX problem because the user is getting a different outcome than what they're expecting. So we know now that the workload mix, it shifts, and we know that transactions are sensitive to the state that they execute on. But what does this mean? Well, for the workload mix, it just means that one dimension can't really do it all, because we see that the workload mix is different across chains, it's different in the same chain, and one dimension can't adapt on its own. So this would require manual repricing if we were to adapt. And when the ratio is wrong, essentially, some resource will be underpriced. In the example, which is very simplified, shown on the slide, you see 2 sample blocks. They both appear full, but they have very different resource profiles. Like in one of them, the compute is completely idle. And with one dimension, you can't differentiate between the 2. There's already some unbundling being done to move away from this one dimension, and other EIPs are being proposed to tackle this further. In general, you want to be able to tackle this without maybe introducing too much complexity. Then the other thing we saw is that transactions, they are sensitive to the state, especially the MEV ones and the DeFi ones. Around 50% of them exhibit variance to the state. This is a UX problem, like users want to know what their transaction will do when submitting it, but it also makes block building harder. For example, when like the transaction execution just varies a lot depending on where you put it in a block. Now, what does this mean for future designs? Well, in the EVM space in general, we have future designs that are being proposed that in general, they increase the state divergence. Like higher throughput, state is going to diverge more because we're processing more per unit of time. Encrypted mempools, for example, they increase a bit of uncertainty, and asynchronous execution also, which Monad has, increases uncertainty, since by the time we're scheduling block n+1, we might not even have the state of post-execution of block n available. Now, at the same time, there's various things in the EFM that sort of assume stable execution paths. Like access lists assume you know what you're going to be accessing. Parallel execution assumes that if you're doing it optimistically, you want the access patterns to not be dynamic so that you don't have cache misses when you're re-executing them. And same for gas estimation, which you have with when this is also if you're charging on the declared limit, which some of the asynchronous execution chains like Monad are doing, you want users to be able to predict this. Now, there's many things already being done to address this, but this is something that we want to bring your attention to, that more work should be done in this direction in order to deal with this uncertainty. So the takeaways are the workload mix shifts, execution varies with state, and future designs amplify both, so we really need to be paying attention to how to deal with this uncertainty. So yeah, then I'll leave you with that the EVM pricing model assumes that execution conditions are stable. We show that they're not, and as the EVM chains scale and evolve, this just needs to be accounted for. Thank you.